So this talk is it's a culmination, it's a convergence of a number of things that I've been talking about over the last couple of years. And if I go to the website, apparently I'm going to talk honestly about success and failure. I won't talk dishonestly about it, but I do want to talk a little bit, rather than just point out problems, I want to point out one of our greatest failings. There is a myth. The myth goes, we learn from failure. Okay? And a lot of people do this, and there's a very good reason people say this, because there is also the idea that failure is failure, and failure is very, very bad. So people naturally take an opposite position. They say, well, no, actually failure is good. We learn from it. And they do this, you can see it with cat memes, it's motivational, it makes you feel positive. The only problem is it's complete bullshit. We can learn from failure is a completely different statement to we do learn from failure. Sadly, generally, statistically, we don't learn from failure. So, I thought it might be appropriate to start with a failure screen. I thought I'd choose somewhere local. It's Copenhagen Airport. About 10 years ago, before GoTo became GoTo, was still Joe. I was on my way, and I found this matrix-like screen. I enjoy the aesthetics of it. I think its portrait, extended portrait profile is quite attractive. The use of white on blue is a beautiful contrast to the surrounding wood. As software developers and as people involved in technology, we are the largest creators of guerrilla installation art on the planet. And so this has kind of become a thing, to the point where I kind of take photographs, and people now send me photographs. They actually tag me on Twitter. And back in 2016, when the timelines forked, somebody started calling it a Kevlin Henny screen. And this has actually become such a thing that at a conference in 2016 in Bristol, where I live, the organizer of Agile in the City said to me, Kevlin, there's a Kevlin Henny screen downstairs. Now, what I want you to do is go down, stand in front of it, I will take a photograph of it, and then I will tag it Kevlin Henny, then you retweet it. Okay, there's a kind of, yeah. And then at 2017's Agile in the City, John took another photograph of me. And then at DevTernity a few months later, you know, it's turtles or fail screens all the way down. And this has in fact made it to the register. Let's see, Kevlin Hennys are frequently seen at ATM machines, supermarket checkouts, but the best ones usually occur at transport hubs, where we enjoy the full benefit of giant displays. Somebody, I don't know who, put it into Urban Dictionary, which gives me some kind of credibility with my kids. So the point here is I've become associated with failure. Yeah, that's an interesting one. And I have quite a few of these collected. The important thing here is that what we learn something, or we can learn something. When a system fails, we lose all encapsulation. In other words, we see how it is structured. We see, as it were, behind the veil. And this is the point that we need to remember. When we are working with computers, when we are programming, what we are doing is we are taking a universal machine that can potentially do anything and turning it into something specific. And it has huge capabilities, but we say, no, this is an application for looking at a conference schedule. This is a way that you can get cash. Anybody remember cash? Okay. This is a machine for playing chess. In other words, we repurpose by specializing. And here we actually see something behind the scenes. We see, it turns out that these things run Windows. And that would be Windows 2000, and that was 2018. It turns out that we also discover that many of the systems upon which we rely are humongously out of date. They are, and we also have a an answer to the question. People say, well, you know, if it works, don't change it. The system's been working. These days we just raise our hand and we say security. Because if it's out of date, that means it's not being supported. So it turns out, interestingly enough, we do have a reason to always keep our code fresh. The bytes don't decay, but the world in which they live moves around. And if something's not being actively maintained, that means that it's potentially exploitable. We learn things about how things are structured. So this was sent to me by somebody in Canada. Many of you may be familiar with the idea that in Canada, large parts of Canada are actually bilingual. It turns out they are trilingual. They also speak PHP as well as French and English. But in failure, a system can reveal itself. This caused a bit of a stir in Canada about 2 years ago. This hit the news in Canada because Cadillac Fairview, a property company, a real estate firm that owns many malls in Canada, somebody spotted a fail screen, and then they looked closely. TensorFlow, okay, certain systems. Face Analyzer, I wonder what that means. It turns out that they had a system that was analyzing passers-by's faces. They wasn't holding specific data, but it was doing large-scale demographic analysis, and they collected quite a lot of data points. People don't like being spied on, it turns out. This caused a lot of noise in the news. We learn what people are up to once the system fails. We also learn that people are really bad at time. I mean, I'm bad at time management, but I've absolutely figured out time zones, and I love the history of date, time, and how we as human beings struggle to try and bring order to the orbital mechanics of the Earth. It turns out that most things to do with time are actually political. And where we add hours, where we add days, where we subtract years and do all kinds of stuff. And this one is a brilliant one, -1 AM. I mean, honestly, if you ever wanted any evidence that you don't want to use a 12-hour clock system, just look at most software failures. Or watch iRobot. The point is that the 12-hour system invites failure. This one's quite good, -1 AM, -1 PM. My favorite one, so obviously time travel is something that I'm quite comfortable with, but not everybody is, except that in software development we do time travel. This is one of the other things that distinguishes us from many other disciplines of creation, design and engineering. We have the ability to travel in time. Most engineering professions do not have that. If something doesn't work out, we just undo. We roll back, we go to a previous version. We literally can travel in time. It is one of the coolest things we do, and we don't talk enough about it. Yeah? If you are asked what it is that you do, you say, you know, I travel in the cyber realms through time. And if you can have a faraway look as you say that, the person with you will either walk away or run away, or be really impressed. Because we do travel in time. That is the thing that we can do. We can alternatively engage in different timelines, which we can't do in the real world. What if we move that building 1 meter to the left? Yeah, you know, that's going to be a big logistical issue. We can do this in software. It's soft, or should remain so. So the problem is it also tells us something about the failures. One of my favorite ones, I bring this one out every now and then, because, I mean, you know, Facebook told me that my feedback would be used to improve Facebook. No, apparently it hasn't. They decided to use my feedback to destroy, you know, democracy as we know it and other things. But the best bit, thanks for taking the time. Yeah, all the way back to 1969. Now, I used to have a theory on this one, but I've got a second theory now. So how do we end up, I mean, why did we end up on the 31st of December 1969? Well, there's a thing at the heart of many systems. We know that they use the C library, okay? And there is a time function in there. And most C implementations, you do an implementation of the POSIX standard, which is listed there for those that care about numbers. And the POSIX standard uses a base, so in other words, no, C is not required to have a particular representation, but people tend to talk about the epoch. And it turns out that in software, we're very good at generating the value 0, even when we don't mean to. This was one that somebody sent me. So we're very good at generating the value 0. So what is 0 from the epoch. Well, the epoch, as was discovered here in another failure screen, apparently there are Intel driver updates for 1970, which is quite impressive, really. 1st of January, midnight. That is the beginning of time. Okay? So for those of us who were born before that, guess what? We are timeless. It's quite cool. So it turns out that if we have an accidental source of the value 0, and then we add time zones, because I was looking at this from the UK, Facebook, all its servers are west of the UK. If you do a time zone adjustment, that takes you into 1969. Yeah, easy time travel. That was the theory that I used to go with. But actually, I think there's a better theory. This one, there's another way of generating this. You just need something that's slightly negative. You don't even need to go a few hours into 1969. You can go 1 second into 1969. If you go and look at the C standard is very, very clear. It's also quite big. When you call the time function, if time is not available, it will return -1, which also happens to be 1 second before midnight. I mean, this teaches us a great deal about API design and how not to do it. But there is an important point here. The assumption, we might say, oh, the fault is the API design. No, the fault is the assumption that time is something that is always available. Time is a resource. It's like a file system, it's like a database, it's like a network. It doesn't mean it's going to be there, but it's always there. When you say that, the universe will hear you. And it will go, ha-ha. And we will get taken back in time to 1 second before midnight. So it undermines one of our assumptions. Now, one of the most popular numeric issues that has, I mean, people now know, to the point that people now think that this is a feature of the web, that actually NaN is a thing. Well, I love this one from Lufthansa. NaN, I'm trying to parse it, but it's not a number. Yes, exactly. How very insightful of you. NaN is popular. It's so popular, people automatically assume that the code is JavaScript. In fact, I had this, interesting enough, yeah, there is a question. We don't actually have a proper name for these bugs, but I did kind of notice this, last year and thought, well, maybe we should call these Batman bugs. If you're not quite sure why that's funny, come and talk to me afterwards. But this is an interesting one. This happened last year. A driverless car slammed straight into the wall after a practice lap. Apparently something got set to NaN. And somebody, one of the responses when I retweeted this, somebody said, oh, are you saying that they used JavaScript to program a driverless car? It has got to the point where people assume this is JavaScript. It's like, no. NaN is a feature of IEEE 754, and that's from the 1980s. There are many things. It just happens that JavaScript is a popular way of generating NaN. There are other sources of NaN as well. If you need factories for NaNs, pretty much any language will give you that. But we have an interesting question here. What can we learn from this? First of all, that's a driverless car. What if you put a driver in it? Yeah, it gets a bit messier. The other thing is, by the way, the language was Mathematica. So in other words, it was a prototype simulation. You don't really want... No, was it Mathematica? No, it's MATLAB. My mistake. Sorry, Stephen Wolfram. It was MATLAB. And so there's an interesting question here. This is prototype code. At what point does prototype code become real code? At what point do we have enough tests to say this is production ready? Another thing that is interesting is that this demonstrates a failure of state modeling. It's one of the things that most developers are not very good at, because most of our languages and paradigms do not have an explicit concept of state transitions and state models. Now, I'm not going to suddenly tell everybody that this is the way to solve everything, but I do notice that half the time that people are struggling, they're looking at a screen of code and they're not getting up and drawing a diagram that shows them what the model behind the code. The code is the truth, but the truth is not always obvious. Sometimes you need to look at it from a different angle. The thing is that all of these techniques are old techniques. We're not very good at learning from what we already know from our successes. We're not very good at learning, I mean, although these days people accept testing a lot more, This paper by Ding Yuan and others from 2014 has a very simple title: Simple Testing Can Prevent Most Failures. But actually, they do an analysis of a number of systems. The most interesting observation in the paper is actually this one. A majority of the production failures, about 3/4, can be reproduced by a unit test. And the point here is that not necessarily that we are able to detect everything in advance, but once we have detected it, it becomes very easy to replicate. And the idea of writing a test for a defect that you have is one of the most important but most overlooked ideas. People often, when they are given a bug, when somebody points out a bug, they'll go and replicate it, they'll dig into the code, figure out what's going on, and then they will fix it, and then they will say the bug is fixed and check everything back in. The one step they often miss, which we could call defect-driven testing, DDT. DDT is for getting rid of bugs. It's also not very good for humans, but let's leave that story to one side. But DDT is a simple technique of increasing the scope of your knowledge, increasing the traceability. Yes, we had this error, and now that assumption, that oversight has now been fixed. Not only do we have somebody's confirmation in Jira that it was fixed, we actually have real code. Jira, whatever happens in Jira stays in Jira. But the code, we have a test that says this was fixed and it's traceable, and we can roll back through time because we are time travelers. We can roll back through time and demonstrate the presence and absence of that bug against that test. That's what traceability means. But it also allows us to increase the body of knowledge. Now these, and I'm looking at code as being a body of knowledge and tests as a body of knowledge. The important thing here is that these are systems that were not necessarily created with unit testing in mind. And yet it turns out that in many cases when people say, oh, it's a big failure, we can't do unit testing. Normally they're wrong. In fact, I'd say, at least based on this, 3/4 of the time they're wrong. You can do unit tests. It turns out that most things have very humble origins. Now, sometimes we have some sort of interesting examples. This is the USS Yorktown, which has been since decommissioned, but in 1998 it reached the news for all the wrong reasons. 1998, it was dead in the water for a few days because they went and replaced their Unix operating system with Windows, which appeals to some people's sense of loyalty. And just to clarify, it was Unix, so if you're sitting there going to Linux, ah, yeah, we're the winners, they were absolutely never going to install Linux on that ship. That was so far down the list of possibilities. No, we're going to take Unix from a respected supplier. So then they took Windows from a respected supplier. Actually, the real problem was not specifically with Windows. I think it's easy to blame Windows. It's another aspect in Windows. The source of the problem on the Yorktown was the data contained a 0 where it shouldn't have. Oh, so what do we learn from this? Validate your data. Check your data as it comes in. Do not trust the things that other people give you. You don't know where they've been. It's like when we tell our kids, you know, don't pick that up and put it in your mouth. You don't know where it's been. Yeah, it's exactly the same with data. And when the software attempted to divide by 0, which we know is a bad thing, a buffer overrun occurred, crashing the entire network and causing the ship to lose control of its propulsion system. Now, the reason I say that it's not necessarily one to blame Windows for is because this sounds like a device driver, because Windows is quite resilient to your application dividing by 0. So in other words, this is in something that is running in kernel mode. So let's talk about writing correct programs. Well, we've always cared about this. 1950s onwards, well, probably in the 1940s, but people started really making noises about how do we do correctness. John Bentley, who wrote a series of columns in Communications of the ACM in the 1980s, Programming Pearls, which he collected together in a number of books, which is really good. He wrote this piece in 1983, Writing Correct Programs. And in it, he explored a binary sort. He presented a binary sort algorithm. Presented it in pseudocode, and this is all good. And he made the point. He said one of the major benefits of program verification. So this is at a point where people were talking about program verification, but done by humans. Now it turns out formal verification is an idea that keeps coming and going, and It's mostly going from the public perception, but it turns out that it's more useful when it is automated. It turns out that the amount of proof required for the most trivial case is enormous. You saw the size of that code. As he says, one of the benefits of program verification is it gives programs a language in which they can express that understanding. When you annotate it with all the relevant assertions, the invariants, it gets a bit larger. This is clearly not something that's going to scale to a system of hundreds of thousands of lines. But the lessons from formal verification are the things that drive many of our automated tools. So we can borrow secondhand, but direct formal verification of most things is not something we pursue these days. But as he says, these techniques are only a small part of writing correct programs. Keeping the code simple is usually the key to correctness. So those of us who've been pushing this message for a while realize it's not a new message. This was 1983. This is not. Every now and then I get accused by somebody saying, "Oh, this is just fashionable agile software craft stuff that you're saying." You know, and I normally point to things that were written in the 1970s and 1980s, saying, "Yeah. I mean, I'll admit that I happen to like the decades, 1970s and 1980s. That's where I spent most of my childhood, and according to my kids, I still dress like it. So I'm very comfortable with that era. But it also is the era when we were saying, you know what? You shouldn't comment everything. That's noisy. You know what? You should try and use meaningful variable names, but preferably meaning that is shared meaning rather than meaning that's special to your own head. And you should try and keep things simple. This was the message of the past. Have we learnt this? I'm not entirely convinced we're doing a great job of that. Now, he said, on the other hand, several professional programs familiar with these techniques. I don't know where he was finding lots of programmers in 1983 who were familiar with formal verification in practice. Well, actually, I do. He worked at Bell Labs. Everybody else in 1983 was not really doing this. But nonetheless, there was enough experience there. He said, I've related to me an experience that is too common in my own programming. When they construct a program, the hard parts work the first time while the bugs are in the easy parts. Anybody who also tests will understand that this is where most of the problems are. Anybody who's ever reviewed code will understand this is where the problems are. We are normally drawn towards, that's the tricky bit, that's the really clever, we better get that right. What about the rest? Don't worry about it, it's fine, it's simple. It's easy. Yeah. There's an interesting thing. Most of the development techniques that we encourage people to adopt, whether we frame it as agile, whether we frame it as engineering, craft, or whatever, are actually about attention management. Now, this was a revelation that came to me a few years ago, and I suddenly thought, oh my goodness, we've created a whole industry on giving people advice on attention management. Because that's what it is. What we're trying to do is keep people focused. I could develop this, this, and this. No, let's just develop this feature until we're finished, until we know it works. Yeah, but I want to do this thing over here. Let's keep it over here. Stop shaving the yaks. The yaks will wait. Let's keep our focus here. Test-driven development. Let's keep focused on this. Yes, but if I add this, this makes it more general. People don't care about general. They want something that works for their specific case. They've already got a universal computing machine. They don't need it any more general. They need an application that does their domain, specially solves their problem. It's attention management. All of these things are just attention management, and we've built a whole industry out of it. It's quite embarrassing, really. But attention management is exactly the issue. When you have focus, a side effect of focus is non-focus. If you are focusing on something, by definition, it means you are ignoring a whole load of other things. It's a side effect. That means that when you're focused on the really hard part, you will miss the really easy stuff. You'll go into that class and you'll say, okay, there's 4 things I need to change. One of them is really, really tricky. And you will get that one right. But of those other 3 or 4, you might forget one. So, this is foreshadowing. This is Java. This is the Java binary search as implemented from Java 1.2 onwards by Josh Block. Josh Block was a student of John Bentley. This is an implementation of that exact algorithm that John Bentley presented. And this all worked fine up until the early 2000s, until people started using very large arrays. Because it turns out there is a problem here. In doing a binary search, you are trying to find the midpoint between 2 values. Okay, you start off with a full range of values and then you halve it. Is the value I'm after in this half or in that half? If your value is in the upper half and you have something that is over 1 billion elements long, then suddenly you are in the range of competing with the limits of an integer, because integers are not integers. They are ints. They are truncated. That's why we abbreviate it. Well, I'd like to think it's why we abbreviate it. Integers are not infinite, but in our head they go on forever. And the problem is, when we add two very large numbers indeed, they make either a very large number or a very negative number. At which point, oops. So, here's the simple thing. This was framed from a mathematical point of view. If one of your colleagues is a mathematician by training, check their code. Okay? Mathematicians, oh yeah, it's given, we can prove this. Yeah, maybe you can, maybe you can't. There's a whole load of assumptions that people bring because what happens in software is we mix different domains. We bring together the domain of customers, we bring together the domain of the machine, there's assumptions about programming languages, there's all of our education and the way we were taught to think, either explicitly or indirectly. So what we discover is this is potentially, when he had this bug was sitting there in that algorithm from 1983 until 2006. And this is an example of what is known as Muffrey's law. You may have heard of Murphy's law. Muffrey's law is actually to do with editing and writing. If you ever write anything correcting or criticizing the quality of someone else's editing, proofing, spelling, grammar, etc., there will be some kind of editorial error in what you have written. You know, if you write something like, you're missing an apostrophe, you will end up using the wrong version of your. English is filled with minefields like this. But every language has this. You will use the wrong something in trying to correct somebody else. Bentley's article was unfortunately an example of Muffrey's law. Here's how to write correct programs, and a bug that stayed hidden for nearly a quarter of a century. Now, how do we fix it? This is the simplest way of doing it. Josh also recommends in his article this. Probably faster and arguably as clear. I don't know, do you want to have that argument? Alberto Savoia wrote in Beautiful Code when he analyzed this bug. He said, probably faster, but maybe obscure to most Java developers, including me. That's the reality of it. But let's actually also look at another assumption, one of the other reasons we get things wrong. Sometimes we're being a bit too clever. Remember, this is another guide to correctness. Bit shifting is also a common source of bugs when people are trying to be that little extra bit clever. But there's this observation in More Programming Pearls by John Bentley. So in other words, this is advice that is over 30 years old. He quotes Guy Steele Jr. If the programmer can simulate a construct faster than the compiler can implement the construct, the compiler writer has blown it badly. Now this is before the modern era of highly optimizing compilers. Somebody in the 1980s is still saying this. Do not second guess the compiler. There are so many little clever pieces out there where people try and second guess what the compiler or the runtime is going to do, and it adds complexity. It does not make it probably faster. It makes it probably more likely to have an error. We should learn from this. We should also learn what Josh observed. He said, you know, the greatest lesson he takes from this, the general lesson, is humility. You know, it's hard to write even the smallest piece of code correctly, and our whole world runs on big, complex pieces of code. And we see this in the everyday. So perhaps that algorithm sitting there in a library doesn't feel like it's your domain, except the fact that you might use it. This is a book called The Making of a Fly, The Genetics of Animal Designs. You can see it's secondhand. I don't know much about genetics, except what perhaps anybody who has an interest in science might know about it. I'm not a geneticist. But apparently this book is one of the ones that you go to. I mentioned this example I'm about to show you to a group amongst whom there were a couple of people whose PhDs were in genetics. And they said, oh yeah, this is a kind of a standard text you learn from. So let's say you are going to study genetics. And you go to Amazon. If you want to get that book new, whoa, 1.7 billion US dollars. Wow, that's pretty expensive. Huh? I mean, I'm sure it's a good book if you happen to be into genetics, but $1.7 million, wow, that's pretty serious. And there's another book vendor that's offering for 2.2. I don't know, $500,000 between them. It's so difficult to choose, when you've got that kind of money. Or you could buy it second-hand for $35. I'll go for the second-hand option. Thank you very much. Now, this was an observation that was made back in 2011. And Michael Eisen looked at this over successive days. He observed it. And he noticed that there was a consistent ratio because there are two vendors. This is not Amazon. This is Amazon being a bookstall market for other vendors. And it turns out that one of them had this ratio. Profnath had this. Now, this is interesting. What does this tell us? This tells us that they have implemented an automated strategy of undercutting the lowest other price out there. It's a standard offer you get in some places, where they say, we're the cheapest. If you can find better, we will, if you can find a better price, we will match it. What they're basically doing is saying, look out there, who else is selling this? Take the min of the set, and then we will just undercut it. We will always just be a few pennies off, 99.83% of whatever is the other lowest. So from this, I learned that Profnath have the book. They actually possess the book to sell. Bawdy Books, however, do not possess the book. They're running a different strategy. What they're doing is they're saying, okay, you buy it from us and we'll buy it from somebody else and then we'll sell it on and we'll make a nice 27.5% cut on that. They are both correct. This is in other words, they have both got a strategy that is testably correct and is localized. Again, we are looking at code from this point of view. We have two individual systems that are individually correct, and when we let them play, they take it up to this. This was before the plug was pulled. And somebody thought, you know what, that might be a little expensive for a book on genetics that you can buy for $35 secondhand. This is an important point. It challenges us to understand, although I've made a play about unit testing. Unit testing is a beginning, it's not an end. Code review is a beginning, not an end. And when I talk about code review, I've discovered these days I need to qualify it. I don't mean that kind of pull request nonsense. That asynchronous code review where somebody else has a quick look, looks good to me, and sends it back. So yeah. No, I mean a proper social experience where you have two or more developers either together on a call or in the same room going through the same piece of code. Your job is not to find errors, to truly understand. It's a knowledge transfer activity. This is the stuff of creating and generating and clarifying assumptions and knowledge. So that's what you're trying to do. This kind of like tick, yeah, looks good to me. It's superficial. It maybe catches a few things, but actually it's not making the best use of this. Collective intelligence is how we develop software. Collective stupidity is how you get Brexit. And the reason I'm throwing Brexit in is because this is an example from October 2016 of a flash crash. Now, the pound was experiencing a very volatile period in 2016, but not this volatile. There's a crash there that occurs over a period of minutes. It drops the value of the pound against the dollar by a huge percentage. Honestly, as a human being, we're not that fast. I mean, we really can't get things that wrong that fast. I mean, I know we try. But human beings are just not capable of optimizing stupidity at that speed. To do that requires software. This is algorithmic trading. This is exactly the same as the genetics of the fly. It's just run over large markets. You have individual algorithmic trading systems, each individually correct with respect to their own assumptions. But when mixed in a universe, you get these collective surprises. It means we need to understand the system level. We need to also pay attention to what some of the safety critical people have been telling us for a long time. Earl Wiener is an expert in aviation systems, and this observation dates back decades. Digital devices tune out small errors while creating opportunities for large ones. Now, I noticed, actually, although it's not entirely correct, this talk is tagged as architecture in the schedule. So let's talk architecture. This is a nice book, Christmas is Coming. This is the kind of book that makes you look smart and culturally aware, and people go, oh, not just a software developer. Okay, this is how you kind of show your broader side to your colleagues. 101 Things I Learned in Architecture School. What's great about this book by Matthew Frederick is about half the advice is directly applicable to any discipline in which we do design. And one of the simplest observations that is offered is a quote from the Finnish architect Elil Saarinen: always design a thing by considering it in its next larger context. I have correctness at this level, I understand the assumptions at this level. What happens when I put it in a larger context? And that context can be a business, it can be a thread, it can be whatever we mean by context. What happens when I take this code and put it in another context? Now, I'm not saying you're going to find all the answers, but you can find more by considering that than if you didn't. Yeah? So, I want to take you, because we're on a time journey here, let's go back to 1996. So that was 2011, we've done 1998, that was the Yorktown. This is 1996, this is French Guiana. This is June 1996, this is the launch of the maiden flight of Ariane 5, one of the world's most reliable and powerful satellite launch vehicles. The successor to Ariane 4, and this is what it looked like on the 4th of June 1996. I would estimate that's probably about 3 or 4 seconds after liftoff. And then this is what it looked like a few seconds after that. One of the world's most expensive fireworks. It's about 300 million euros worth, the estimated cost to everybody. It scattered parts of the cluster mission over the forests of French Guiana, which I'm sure did not need extra satellite garnish at that point. Now, what caused this? There's a little piece of code here. So this is Ada. There's a whole load of really interesting things if you try and review this code. It's Ada. Some people think it looks like Fortran. There is actually a term for this. It's called Adatran. It's when Fortran programmers speak Ada, they speak it with a very strong accent. And they're really not taking advantage of the Ada language here. You'll see repetitive code structures, because if it works once, if I wanted to work again, I'd just copy and paste, right? There's some curiosities here. 32767, we've got that hard-coded. Apparently that number is not available in the system, and well, actually it is. It's the upper limit of a 16-bit signed integer, and actually you can ask an integer, hey, guess what? Could you just give me your upper limit? And for some reason, we like it so much that we represent it both in decimal and in hexadecimal, because, just to be sure. Just in case we got the decimal wrong, we'll check it again. What we're doing here is we're thresholding. In fact, in sensible modern languages, we call this clamping. We have it as one function. We clamp if value's too large, we threshold it. Too low, we threshold it. Otherwise, we let it pass. You will also notice that in some cases, this does not occur. There is a type conversion here. And this type conversion is unchecked. There is a very simple reason that this type conversion is unchecked, is because there is no way that this can ever exceed the maximum value in an Ariane 4 launcher. If you are listening carefully, you will notice I just said Ariane 4, not Ariane 5. This, folks, is what we call code reuse. This code works in Ariane 4, and it plays a role in Ariane 4. And they simply reused it in Ariane 5. There is a small problem. This code is not necessary in Ariane 5. It is dead code. It is not actually used. The functionality embodied by this code now belongs in ground control. So the functionality has been moved, as it were, from client to server. Okay? So it's now part of ground control, but it's still running. The other thing you need to know is that this is a velocity conversion. Remember I said that Ariane 5 is a powerful launcher. It's much more powerful than Ariane 4. Which means that it exceeds the limits that we assumed would never be exceeded. And that is how you trigger this, because this is the self-destruct system. That software works. The rocket went out of control. You don't really want a missile out of control, so therefore the self-destruct system kicked in. Now the point here is there's an assumption. There's also something else. How one piece of code will call another. The relationship between modules, the relationships between services, the relationship between functions. It's not just about the obvious dependencies. It's about some of the things we find hard to articulate. Assumptions are very curious pieces of knowledge. An assumption is like a Lego brick on the floor in a dark room. Okay? You don't know it's there until you know it's there. Okay? I am assuming we're talking barefoot here, okay? You're walking into the room barefoot, and then you know, even if I told you, guess what? There are Lego bricks on the floor. Guess what? You will have assumptions about the piece of code you are working on the system you're working on. Even when you know you might have assumptions, that doesn't tell you where they are. It just tells you that there are assumptions. And why I say it's a curious piece of knowledge is if I asked you to list out your assumptions, you wouldn't be able to do it. An assumption is discovered most often in contradiction. You discover it by having it contradicted. Though that moment when you go, oh, I had assumed that, at that moment you learned that you've had this assumption perhaps for years. You've had that knowledge for years, but there's no way you could have discovered it until it came in collision with reality. So there's a point here as well. Dead code. Do something with it. Let your version control look after it. You don't need to keep it. And then people often say it doesn't cause any harm. Well, actually it causes hundreds of millions of harm if we actually add it up. So let's stick with rockets. Let's move to 2017. November 2017, I think. This is, so we're in Russia here. This is a launch of, how many satellites? 19 satellites. Fails to launch from Vostochny. Vostochny is in the far east of Russia. As you can see, it's quite cold and quite snowy. So how did they lose the whole vehicle? How did they lose 19 satellites? Well, it turns out that the upper everything, all the hardware worked. So if you're a hardware person, well done. But almost unbelievably, the flight control system on the Fregat did not have the correct settings for the mission originating from the new launch site. The new launch site, it turns out that most launches by Roscosmos in Russia are either in Baikonur in Kazakhstan or in Plesetsk, which is in it was in the east, sorry, the west. Let me get my geometry right. I'm trying to reverse things for you as an audience, but I've over-reversed. Yeah, Vostochny is in the far east. In the west, we have Plesetsk. They moved to the launch site. They forgot to change the details for the third stage. Stage 1 goes up and says, I'm on course. Stage 2 goes up and says, I'm on course. Stage 3 says, oh my goodness, I am on the wrong side of the planet. I am so far away from where I should be, I better burn some fuel. And it did. And it re-entered the Earth's atmosphere somewhere around Iceland, where it was spotted by a British Airways flight. In other words, it's just like, I need to get back to where I'm supposed to be. Oops. So that piece of software, now here's the question, is that a coding error or not? And people say, oh, that's just configuration. So here's a paper from Tianyi Zhu and others, also from Usenix. This is a paper from 5 years ago. They make an observation, early detection of configuration errors to reduce failure damage. What they observe in a study of a large number of software systems, many of today's mature, widely used software systems are subject to latent configuration errors, LCEs, in their critical, important configurations. Configuration errors are often not detected until late. And people don't consider configuration to be code. Oh, that's just configuration. I actually wrote something on this last year when I was talking. I wrote a piece on paradigms and thinking called Out of Control. And I raised the question towards the end, what then is configuration? Because many people kind of have this box in their heads. They don't know they have this classification. They go, there is source code. Then there is test code. That's not really part of this. And then there are scripts. They're not part of this. My job is source code. And this is the system. And then there's these other things that are kind of necessary, but they're not as important because they don't actually run on the target machine, or they're not Turing complete. There's configuration. That's not real code. Configuration is a formal structure for specifying how some aspect of software should run. Configuration is code. I don't care what your opinion is. If you think that configuration is not code, your opinion doesn't matter because you are wrong. Okay? I'd normally like to be very open about various things, but there are certain lines. You're using a formal notation to describe how a system should run. What is not code about that? So here's an important consideration. Even though it might not be Turing complete, it's a formal structure that is used by your code. And it's in our blind spot. It's out here, so we forget to test it. And we downplay the significance until you lose 19 satellites. What we discover is one of the first things I ever learned in software, garbage in, garbage out. In fact, this observation, it goes back to Charles Babbage, who did not coin the phrase, but he made this wonderful observation in the 19th century. On 2 occasions, I have been asked, "Pray, Mr. Babbage, if you put into the machine wrong figures, will the right answers come out?" I am not able rightly to apprehend the kind of confusion of ideas that could provoke such a question. And yet we engage in this every single day. It's called a spreadsheet. You want to know what runs the planet? Spreadsheets. And here's an interesting quote from Stephen Levy. A Texas-based oil and gas company had fired several executives after the firm lost millions of dollars in an acquisition deal because of errors traced to a faulty financial analysis spreadsheet model. Now, we're not saying that the software of the spreadsheet was wrong. We are saying that the configuration, the data and its relationships was wrong. We need to recognize that that is first-class code. We also need to recognize that this is not new, because this was 1984. This is an old problem. This is back in the early days of spreadsheets. We already knew this was a problem. These days, we tend to put everything on Excel. Always remember, Excel is a functional programming system. So, this upsets Haskell programmers greatly. The issue with Excel is its type system. It is a functional system, but its type system invites and encourages errors. Do we know how to solve those errors? Yes. Whenever I use a spreadsheet, I am always stunned at how incredibly bad the user interface is. Now, I'm not talking about grids. I think grids are great. I think they're such a powerful mechanism. And yet when I compare that to developer tools or even word processors, the support the user has for finding problems, or the support the user has, the support it gives the user for creating problems is astonishing. And they have not bothered changing this. Normally, spreadsheet vendors will come out with some nonsense about, oh, we don't want to upset our customers. Really? I'm a customer of Microsoft. You upset me on a regular basis, Microsoft, by making changes that are not necessary instead of the ones that are necessary. And I'm not going to pick on Microsoft. Hello, Google. The point here is this is a known problem, has been a known problem for decades. It is actually relatively easy to solve, but nobody's really said, oh, we need to solve this. They have not seen it as a priority. We see also, for those people who doubt that it is a programming system, guess what? It is now fully Turing complete. Okay, Excel now supports true lambdas. You can do full lambda fun with them. Currying, partial application, church numerals. Please don't do this. But also, Excel has it has 2 programming systems. It has the programming system within the grid. I want to say within the matrix. That sounds cooler. Within the matrix. And it also has VBA, which is a programming language, honestly, really. We'll see some in a moment. The type system does these automatic conversions, which are unnecessary, error-prone. I mean, they are unnecessary. Nobody ever wants them. I've never found them actually useful. And they are easy to make right, but nobody bothers because you're just customers and you're already bought into Excel, so why bother? Gene name errors are widespread in the scientific literature. This has been something in recent years that people have focused on. A sample from the paper. You see all these things, SEP2, SEP3, SEP4, OCT3, OCT4, SEP1. These are all gene names. They also happen to be months or dates, and they get automatically converted. Even when you say, this is just a general field, by default it says, oh, I'm not going to treat this as a general field. I'm Excel. I know what you're trying to do. No, you don't. Just leave it alone. I'm trying to put stuff in a grid here, okay? It's got to the point where actually this is huge. 1/5 of the papers with supplementary Excel gene lists contain erroneous gene name conversions. We are talking about the stuff of life that's been accidentally converted. I mean, we're not talking Jurassic Park here, but... So, they actually went, Excel errors have forced a whole scientific discipline to change its practices to avoid the problems with Excel. That's how bad it is. We're halfway through the COP26, the United Nations Climate Change Conference. Well, there's still some people out there who kind of trying to deny that things are going on. And there was an interesting thing that was published a few years ago that tried to highlight that if you decided to look at the Earth's temperature and you used a different version of average, you got a cooling instead of a warming. Now, let's be very clear about this. You don't get to choose the average. You don't say, today I shall do this using the mode. Tomorrow I shall use the root mean square. My mood on Friday, I don't know. Let's see what average I want to do. Maybe I feel like using the median on Friday, or perhaps the geometric mean. I've never used the geometric mean in practice. Perhaps that would be exciting. Maybe I'll get different numbers. The laws of thermodynamics are defined in terms of the arithmetic mean. It really is that simple. But what they said is, look how what happens when you take the quadratic mean, the root mean square. It cools. So in other words, whether or not the Earth is warming or cooling is a function of which average you like to choose. So when summer comes around next year, don't be fooled by the weather. Say, what average shall I use today? And you may discover that you lose a couple of degrees just by choosing a different average. It doesn't work like that. Also, if you know anything about statistics, you will know that the root mean square is always higher than the mean, because the quadratic mean, equivalent to the root mean square, is the arithmetic mean plus something related to the variance. It is always higher. If you get a result like this, you should be able to say, wait a minute, there's something wrong here. I've done something wrong because the root mean square is going down instead of up. And this was originally taken from a critique of a couple of climate change deniers, Christopher Essex and Ross McKittrick, who published this in a book without any peer review, and he picks up on a number of corrections. But even then, he doesn't get all of the issues that are wrong with this. What I find interesting is they basically use this to find out the mean. Excel has a function built in called average. It doesn't have one built for the root mean square. You've got to write that for yourself. They didn't write this because they're not programmers. They didn't write a function. What they did is they ended up doing the old, we'll create a large complex formula and then copy it from cell to cell. However, I've taken the effort to turn it into VBA. This is because I'm a programmer. This is what they implemented to calculate the RMS. I'd say there's nothing wrong with this, but you need to look at the context. We're looping through cells. We do correct offset Kelvin to Celsius. We do all of that stuff. That all works. And we take the cell value. That's good. Let's look at the context. This is part of the spreadsheet. I got this copy from Tim Lambert. You'll notice there are empty fields. Huh, that's interesting. I wonder what happens when you apply my formula to an empty field. What happens when you get that? Well, it gets substituted with 0. You see, the built-in average function knows to skip empty fields, but unless you write it, you won't get that. You will end up with everything suddenly being a lot colder, which pulls the value down. So yeah, this is how you write it correctly. And then you discover that actually you get the rise that you were expecting. So this misinforms people who are in the denial space, but it also misinforms people who make decisions about finance. This is the paper published in 2010 that led to austerity economics. Reinhardt and Rogoff, Growth in a Time of Debt. This paper is famous and infamous because it basically said that under certain circumstances, certain debt ratios, it is likely that a country's economy will shrink by a small amount. And this triggered a lot of people, a lot of countries into doing what we call austerity economics. This has been roundly critiqued, but one of the most important things from this paper is they discovered that there was a spreadsheet omission. They missed out 5 rows of data from their calculation. When included, it turns out you get growth, not shrinkage. What are the consequences of this? Well, in the UK, the Institute for Public Policy Research did some checking on the numbers. A decade of austerity has resulted in cuts to public health, prevention and mental health budgets in the NHS and wider national and local government services, which help drive better health. Had the trend from 1990 and 2012 continued, we estimate there could have been 130,000 deaths averted between 2012 and 2017. That is huge. Again, this is foreshadowing. And what I'd like to leave you with is this point. Jorge Santayana, which is George Santayana, made this observation that is variously quoted and misquoted. Those who cannot remember the past are condemned to repeat it. We keep talking about these failures. We keep saying we can learn from, we keep saying we learn from failures. No, we have the possibility of learning from failures. But to do so requires a conscious, explicit effort. And I'm afraid some of it's going to be really boring. It's a case of like, oh yeah, those practices people keep banging on about, they do actually make a difference. It turns out that they do actually move the statistical needle. They have a consequence for individuals and for companies. But one of the saddest things, moving to a different George, Georg Hegel, is this observation. What experience in history teaches this, that people and governments never have learned anything from history or acted on principles deduced from it. Summarized by some people as saying, the problem is if you learn from history, you are doomed to watch others repeat it. Thank you very much.